part 3 today. And then let me go back to these here and all right, so I'm gonna call these start now, create broadcast. Sorry, I'm just starting the stream on X, and you know the mechanics of these. Okay, so it's late here. Sometimes when I do streams late at night, it happens so that my baby wakes up and then I have to take a break and then I'll come back. I'm just warning you, if you see a be right back in a bit, it's because of that. So having said that up front, let's get started. Now the live stream is on and the timing is there, perfect. So I can focus on this now. I can have this here and open chat. All right, today I'm gonna do, I was looking at the sessions, and first of all, I was looking at the sessions, and then I wanted to take a look at, I was thinking, should we continue doing the basics or should we do something else? So here, what I've done here, basically so far I've touched upon the linking mechanism, I've touched upon the proof of history a little bit, but I'm not too happy about these. Nevertheless, I think I'm gonna skip and I'm gonna work on the wallets and the transactions thing, because it's something that I don't know. Well, I know what wallets are, I know what transactions are, but essentially I don't. Yeah, it'll be interesting to understand a bit more about these, just because there's a bunch of things in here, right? So we have the real-time market monitoring, the coding of the trades. I think what's interesting is, I mean, as much as this looks like we're making slow progress, it's important, right? Because we are actually supposed to learn these from a first principles perspective. I can go and ask Grok to code one bot for me. That's good, but if I wanna learn this myself, I wanna understand the inside of how things work. So, and blockchain basics are not a bad thing to know anyway. But today we're gonna do a detour, and we'll just jump to wallets and transactions just to kind of take a bit of a break from the basics. Teaches secure key management and transaction building, the foundation for all the bot actions. So we will start this session, and today I am feeling like a Greco-futurism as the vibe for the session. And what I'm doing is I'm gonna plan, and actually, you know what, I think that's a good thing here as an optional thing I should offer here. Always one of these sessions I come up with new features, so features. So one would definitely be add a desired time constraint blocker, maybe Pomodoro style. It's because you will see the think aloud protocol is quite intensive. So when you're doing a lot of thinking and you're doing out loud thinking, you get tired fast. And but yeah, so we'll skip these and we'll go straight into that. Let me turn the microphone on. Perfect, it's working well. So we get back to what's the transaction. Curious to see how it fits into the systems and architecture we touched before. What draws you to this topic right now, and where would you like to begin? I'm wondering about this part. So how do you multi-signature requirements alter transaction fees in ways that single signature wallets avoid? Wait. Let's first, so we're in this step now. We have multiple steps for this session. So, and that's maybe something that I am told is not too obvious in the application, that this is basically multiple, that these are like kind of chapters. Maybe I should put more like chapter 1, chapter 2 title, something like this, or you know, I think I should label these chapters. Okay. Digital wallets and the role in managing keys. Well, all I know, to be honest, is I only know that a digital wallet is kind of like, I mean, what you have an address, right? This address is then something that I guess is just registered in the blockchain somewhere that someone got this address. I don't know if addresses are valid or not. So what I'm gonna do is, can we start with something a bit more basic even? So how do wallets work? Holds a sense value. I mean, so what I imagine happens is it nothing like the wallet is not an existing thing, right? So a blockchain is just a ledger, and so it's basically a list of transactions, and so you can calculate from the list of transactions in the accepted history what the balance is of a wallet. Exactly, ledger holds everything. So what does the wallet itself need to keep track of to let you spend from those past transactions? It needs to at least have the history of transactions related to the wallet. What actually lets the wallet find and claim only its own transactions in that full ledger? What actually lets the wallet find and claim only its own transactions in that full ledger? I guess it's I guess this would be the address. Okay, to create a valid spend from it, it needs, okay, so yeah, I guess it needs your, like, I guess what this is going, so the way that I know this works is it needs your private key, right? It needs something that proves that the wallet has, like, whoever's trying to do a transaction has the authorization to do that, right? It's the key that holds access to that wallet, although that wallet does not really, it's not a physical thing that exists. So does the blockchain then check to confirm that signature is valid? The blockchain has, it's like a private key. It's like a public private key thing, right? So essentially, the private key is all you need to basically verify that you own the wallet. No, yeah, no, it has a public key, doesn't it? Like, how does the blockchain turn that public key into the address it checks against? To be honest, no idea. Let's get some. Let's go get some resources on these. That is definitely a gap that is spotted. So maybe one thing that we could add to make it more easy is that I'm just like thinking out loud. Okay, so what we could do is, spotted a gap feature. So that would then maybe somehow, the way you do this now is you can click on resources and it's going to actually pull resources for, oh no, actually I want resources from a specific question. Okay, So actually, that's what maybe it does, right? So I won, but I won resources from these. Let's look at the Wikipedia link. And then, so cryptocurrency wallet is a device, physical medium, program, or online service which stores the public and or private keys for transaction. In addition to these functions, yeah. So the private. So okay, the. You know what? I think what is helpful. I think that as part of it, yeah. I think. What should happen is, and that's an interesting feature. I don't want to necessarily read through these. I would like to just ask directly a question. And then get the answer. You know what I mean? So I'd like basically like a gap mode or something like this. Gap mode. An actual grok chat, for example. Anyway, let's read through these. Let's read through these for now. So let's read through these. History, types of wallets, cold storage, paper wallets, multi-signature wallets, technology. Yeah, let's go through these. So a cryptocurrency wallet works by a theoretical or random number being generated and used with a length that depends on the algorithm science. These numbers converted to a private key using specific requirements of the cryptocurrency algorithm requirement. A public key is then generated from the private key using whichever cryptographic algorithm is required. The private key is used by the owner to access and send cryptocurrency and is private to the owner, whereas the key is shared with a third party. So at this stage, no computer or electronic device is required, and all key pairs can be mathematically derived and written down by hand. The private key in public key pair known as an address are not known by the blockchain or anyone else. The blockchain will only record the transaction of the public address when sent to it. So essentially, is then the public key. So the public key is generated from the private key, which is then generated from the address. Huh. Well, I would say what makes sense is that, okay, the private key is created first and then the address, right? Whatever is created first is whatever is the most private thing. That's what would make the most sense. And everything else should be derived from that, because then you only know that. And so because you know that, then you can generate the address via some sort of like one-time like hashing or something. I don't know. Yeah, private key first. Everything else is right from it. Where does the public key fit in the chain before reaching the address? The public key. That's an interesting question. To be honest, let's think about these. So you have a private key, and then it is generates an address, and then from the address you generate a public key. Does a public key even have a utility in the blockchain sense? It does. So a specific job does the public key perform when a transaction gets checked on the blockchain. Okay, with the public key, well, okay, the public key is then something that can be used to verify that the. So is it? Let me sketch these. So is it that basically you have private key, then you do wallet, and then you do public key, because what the whole point of the whole point of private public key thing is that when you, like in regular cryptography, when you are encrypting a message, right, with a private key, so you use a private key for these, and then you're no, the other way around. Like the whole thing with cryptography is you have the public key of the target person, you use that to encrypt these, and because you have the public key and the other recipient has a private key, yeah, it's the same thing, right? I guess you use the public key to sign the transaction. No, makes no sense. No, makes no sense, because here it's more like, why would you use a public key? The public key can be used to verify the wallet somehow. Why would you use a public key actually? Allows others to make payments to the address derived from it. But isn't then the, okay, so isn't then I think I need a quick clean button. Okay, so isn't the wallet the public key? Let's then verify that you are the owner. Proves the ownership. Well, part of the public key check makes it impossible for anyone else to fake that proof. To be honest, this just makes no sense to me, because the public key is a key you can share. So if anyone knows it, they can. It doesn't really matter, no? But I mean, proves that. Well, because. Why would you. Like, if I know, like, it makes no sense at all. Building all what you know about wallets and keys. Try sketching on the canvas how private keys used to sign versus how the public key verifies it. Oh, they verify a transaction. They verify a transaction. That's what you're saying. Am I that dumb? I just feel like I feel very dumb right now. So they verify, a public key is used to verify a transaction. Why? So you would have a private key that generates the wallet and generates the public key. Then the public key is used, okay, because no, makes no sense. You sign it with your private key, not with your public key, right? Makes no sense. Signature proofs ownership. Well, part of the public key check makes it impossible for anyone else to fake that proof. I guess I just need to go look it up then. key derivation, sequential deterministic hierarchical concerns. I'll just ask Grok. What's the time that we have? Okay. The private key, the public key is derived by from the private key, yes. The address is usually a hash of the public key, okay. You get transaction data, you compute a hash of the data. You use a private key to produce a digital signature, yes. I know the private key that corresponds to this public key and I authorize this transaction. How the public key verifies the transaction? Extract the public key, recompute the transaction hash, the signature verification algorithm using the public key, the signature, and the transaction hash. So the math checks, so a signature could only have been created by someone who knows the corresponding private key. But how does it, but what's this math then? Oh, sorry, wrong keyboard. Okay, I didn't know this. That's interesting, actually. Look up. Okay. Oh, cool. It's suggesting Grokpedia. But I should just have a Grok as a tool, I think. I almost think like I should just have a way to access a tool only when I do have that gap. You know what I mean? Okay, so, okay, let's go. Let's dive into these. All blockchains use the same curve, okay? There's a publicly known base point G on this curve, and the order of the curve, number of valid points, is N. So private key is a secret random integer, private key. Public key is a scalar multiplication on this elliptic curve. Anyone can compute Q from D, but nobody can compute Q, but nobody can compute D from Q. Exactly. Signing a transaction, what the sender does. So M is the transaction data. We compute an R point, pick a random secret nonce with a random point. And the math that I ask about is you take the public key and the signature and the message hash. So compute the modular inverse of S, compute two scalars, compute the point, compute the point, and then check if these, the x times the point is mod n. If not, reject the transaction. Wait. Only someone who knows D can produce an S that makes this equality true. Wait. Okay, so you have, without diving into the math itself, you have the public key and a signature. Signing, okay, so because signing the transaction. signing the transaction, there's a random secret, then there's a point. This point is used r equals xr mod n, whatever n is. Then you have the hash, which is m, which is basically the like a SHA-256, yeah. And then you have, at this point I should be actually sharing my screen probably, but anyway, then you have so I wonder if actually one thing that I'm got the logs here. I'll just check these tools. Okay, cool. I'm just monitoring some things. I'm just checking. Okay, going back here. So, and what's the time now? We have, so we've got now 26. Okay, so key generation, private key, the whatever public key is basically, okay, so you take G, which is like a known point, and then do D, which is a secret random. Yeah, it's basically a private key, and then that turns into the public key. But then you obviously don't know these. Anyone can compute Q from D, but nobody can compute D from Q. That's all good. Then we take M is the message, it's a transaction data. Then we have another secret. We create another point. Exactly. Okay, so we create another point in the curve, right? It's the same like the public key, really. We're creating another sort of point in there. And then what we're doing is secret. So we're taking the x coordinate of these, mod n, and that is r. So that's the point. Then we hash the message, and then we calculate an s, which is basically what is the k we've peaked inverted, the message plus r times D, and D is the private key. So then you have the signature, which is R and S. All right, verification. So you have the signature, which is R, which is this random thing you calculated here, and S, which is the result of combining this random thing with your private key. Then adding the hash. And also this random choice here. Message hash. So essentially what people have is they have the public key, they have Q, right, which is DG. Where is Q even used here? In the signing transaction, it's not used at all. Then you have the signature, RS. Oh, okay, it's not used, but D is used. All right. D is used. Whatever you use to create the public key is actually used here as the same factor that you're using to create. No, that's here. Yeah. D. Okay. And so then if this equality holds, all right, so this is, yes, so this, what this is happening is because we're using D And we only know D if we are, if we chose, like we're using the private key. Yeah, exactly. So because we're using the private key, not the public key to sign, but then D is also used in the public key. And the public key is known, so essentially we can do the calculation using Q. I see. Okay, the beauty here is that we know these, we know DG, right? And I'm not going to go through the details of these. I can do that in another session probably. That's worth it. But essentially, yes, now I understand. So it's because we're using because we know the public key, and the public key actually is computed using the private key, then there is an operation we can make on that signature that essentially guarantees that you know that we use D. Hence, you know the private key. That's pretty nuts, actually. It's quite cool if you think about these. You compute these two scalars, which is E and the inverse of S. This guy here. Then U2, which is R and the inverse of S. Then you compute a point, which is basically using this linear combination of G, which is the known thing. It's the known point. And then Q. And then check if the x of this point equals R. So essentially, yes, you've put in here a Q which cancels with this D, right? And so you're making it cancel. You don't know what it is, but you're making it cancel. This is pretty nuts. Okay, so I think I'm ready for these. So essentially, we know these because you can make a calculation. Let's remove these. So we know we can verify the transaction because there is a math you can run that essentially cancels out D and cancels out a component that is what exactly you're using to create the private key of that public key. So you can prove it without knowing that number, but you can prove it because you know that it mathematically cancels, and you can prove the equality. That's the essence of it. Yes, the method lets you prove possession without revealing the secret. What exactly gets multiplied or hashed in that equation to bind the signature transaction stuff is whatever, like a number. I don't think that really matters. What do you know already about digital wallets and their role in managing keys? But I think that's pretty much it. I think so. I think I can mark this one as done. Oh, that actually doesn't work. Why does the done button not work? Okay, I'm gonna pause it. I'm gonna mark it in the next session. Okay, but that was good. We've learned something. Sorry, I know it's a little buggy still. I'm still testing it, to make sure that it's good. But I mean, okay, what's next? The next is write down the key differences between a hot wallet and a cold wallet, including one security example for each. Okay, we'll do that in the next session. Nice. Cool, guys. See you tomorrow.